again. Okay, next talk will be given by Xie Xiaofeng. Li Xiaofeng. Okay. Let's work with Xiaogang.
Okay, everybody. Today I am proud of giving a presentation here. This is my topic, and today's presentation is mainly based on this paper. It's produced by my advisor Xiaogang and me and my senior classmate. And this is my outline. First, I will give some introduction about what is CP violation, because my talk, because this research have a strong relation with the CP violation. And now I will talk about these two processes, the Meson decay to K-on and Pi-on, which motivate us to study this paper. And then now I will give a estimate for breaking effect on SU3 flavor symmetry. Then finally I give the similar relation for other decays, and finally give a summary. Okay, so first, what is CP? Actually, CP can be illustrated very simple. So first, you can think we have some system which have a positive charge and a minus and a negative charge is counterclockwise. P means you reverse the space, so you rotate from here, change to here. And the C in the original just means change the charge sign of charge. So we can change the positive charge to minus charge to positive charge. But in the particle physics, this means we change the particle state to anti-particle state. And the CP will just do the two things. And we know, actually, this is very famous. The CP and the CP symmetry actually are preserved in the gravity and the electromagnetic force. However, this is also a famous thing that CP and the CP has been broken in the weaker interaction. And so, why the CP is very important? Actually, they can explain. The CP violation is a necessary condition for matter and antimatter symmetry. It's very famous, called Shakarov conditions. And this is some famous experiment to show how to break the P, C and the CP violation. For example, the Cobell 16 experiment and only the left-hand neutrinos exist in nature, and the neutral K-on system oscillations. The next problem may be how to produce the CP violation in the Senna model. There are a famous mechanism called KM mechanism, which is proposed by the Kobayashi and Masukawa. And they just to introduce this KM matrix, and you can you can pay attention to this factor, the delta. We call it a Dirac CP violation phase, which is come from the two reasons later it becomes true. The first is the general complex required couplings. Because the required coupling is complex, so we can have such a complex term. And we need to the misalignment between the flavor and the mass eigenstate, which later we can introduce the CK matrix. And they have two important properties we will use in this work. The first we call unitary triangle. Because the CK matrix is is a unitary matrix, so we can have such a relation, which we can just do it very directly to times it. And the other we call it just Cocker invariant, which means that we have some quantity which is invariant, which is independent to the parameterization way. And we also can write down the such a triangle to illustrate. For example, for this we can just draw it on the complex coordinate, which just can be a triangle. And the just Cocker invariant actually is just present the area of this triangle. Okay, so and the next is our motivation. From the recently LHCP data, we have first measure first directed CP relation in billion S decays. And in here, this is ACP. And ACP's definition is that the decay rate of the antiparticle state minus decay rate of particle state, and divided by the sum. And from this definition, we can quickly understand if this number is not equal to 0, then there are CP violation. And actually we have this. And they have an interesting relation like this. And from the theoretical prediction, if we assume the CP violation source only come from the CK matrix and the SU-Swift level symmetry, which I will talk more clearly in the later, then we should have this relation. And from these two data, we have this, and you can see the number actually not far deviated from 0. So this is more motivated us to study, because from this relation, actually we can test two physical facts. The first fact is do the CP violation only come from the CK matrix, only come from the K mechanism? Are there any extra CP violation come from the other mechanics, which we will call it the new physics? And the second, we can test the SU-Swift level symmetry, which is just approximate level symmetry, but physics, elementary prior physics, usually use it to do some work or to derive some prediction. So we can test this assumption is good enough or not. Okay, and in now this formulation equal to this formulation actually can be transformed to this form. And then here delta is defined like this. In our work we mainly use this form. Okay, and now so maybe the first study want to select how to calculate the ACP, or if we want to predict some interesting relation, we will just directly predict ACP. However, for example, in this process, we have two problems. The first problem is at the hadronic level, actually the QED, not QED, the QCD is become a non-perturbative theory. And the second problem is the n-body problem. The second problem is that people actually don't know how to calculate the n-body system. You can see in here we have many quarks. And we can say that actually these two problems is the dynamical problem, because we don't know how to calculate the dynamical property in mesons, no matter the B mesons or the pi or k. So we need to use another method. Another method, we need two theoretical tools. The first is OPE and the SU-Swift. I will first talk about the SU-Swift. SU-Swift means the SU-Swift level symmetry, and it comes from like that, because this is the Lagrange for QCD, And you can see if we don't have this Meson, this QCD actually is invariant under the flavor transformations. So we can have SU3 flavor symmetry. However, actually the quark actually have mass, but because the lambda QCD scale is 1 GeV is bigger than the light quark mass. And I'm sorry, I don't know why this is be cut. Sorry. In computer is okay. Okay, so for example, in our Meson, in the Meson system, the Meson quark is very heavy, so it don't not use the SU3 flavor symmetry. However, for light quark UDS, we have some approximate SU3 flavor symmetry, and we just to take the B quark as a flavor singlet. And so in here we have a triplet. Because the UDS quark is a triplet and the B quark is a singlet. So when we combine these two, we get a triplet. And if we combine two light quarks, we can get another famous architect we call the Meson architect, like it's for some light quarks. Okay, and now we have such a flavor. We have such a flavor symmetry, and we use another theoretical tool called the operator product expansion (OPE), and it is proposed by another proposed. It is a very detailed introduced in this paper, and we just say that the decay amplitude can be combined by some effective operator and some coefficients. And this is effective operator actually come from this Feynman diagrams. And now we can see that, for example, from this Feynman diagram we have such operators. And this operator, because we have three light quarks Q, U, U, so we can decompose it into the more basic fundamental irreducible presentation. And we can say that the irreducible precipitation have a different contribution for this Meson decay process. So we can separate it. And when we use it, and from this diagram, and we can write down the decay amplitude like this in here. In here, T and the P means the tree diagram or penguin diagram. The penguin diagram is just like this. We call it a penguin because sometimes people think it like a penguin. And in here we have different coefficient corresponding to the different irreducible presentation. For example, for 3 or for 6 or for 15. And then in here, A means the annihilation contribution. This is because we can just more intuitively to think this combination like an annihilate, because the B and through some coefficient and become the two light quarks. And the C we just call it a non-annihilation contribution because it is a combination. It's the B combined with the M and combined with some vertex and with another mesons. And in here the H is come from the we call it the Hamilton in the Hilbert flavor space, and it corresponding to the weaker integration structure and the transformation property for SU3 symmetry. And for Q equal to D and Q equal to S, we have a different number. I show it here. Just show the non-zero part.
5分钟.
Oh, only
20 minutes plus 5.
Okay. So sorry, I forget time. And now in here for this process, you can see we have this, and we have this amplitude, and when we use this amplitude to calculate, and finally we can have this formula. And in this formula, because if we estimate SU3 breaking effect, want to estimate SU3 breaking effect, we can find that if the RC deviated from 1, then we can say we break the external model prediction. However, we from the theory or from the experiment, it's an experiment, it's a theory. We just find that the RC actually not deviated from 1, so we can give a give a conclusion is that the more precise data and the reliable calculation are needed to test the snare model prediction. And we needed to pay attention, needed to note that in here the snare model prediction have 2 parts. The first part is the SUC flavor symmetry, and the second part is the K mechanics, or we should call it the Decay matrix. And now we also do for the other process, and do the other process, and now finally we have this table, and this table means that in here is from the experiment, and when we use the relation we derive, we can predict another the right-hander value. For example, in here we can from experiment we can get this value, and we can use this to predict this value, the other value. And we can see if this number is not very different from the experiment, then we can say this relation still hold. And we do these 2 things, and finally I give a summary. Is that we use the OP and SUC flavor symmetry to create some interesting relation on Meson decay into 2 right mesons in snare model. And the relations which motivate us is very is hold well. However, we have discovered that the other color we also study may have broken the snare model prediction. But this broken is come from the SUC flavor symmetry broken, or come from the broken break the K mechanics is we still don't know. So we need the more precise data and the more reliable calculation to test it. Okay, thank you very much.
Thank you.
Thank you very much.
Questions? Yes.
What is SU3 flavor symmetry, and what is the relation to the C violation, P violation, CQ violation?
Oh, actually, SUC flavor symmetry just mean that in okay, maybe we can say more simple is that in QCD, the because the mass of the light quark is very light, so the strength of QCD and these light quarks are same, so we can have some symmetry, which is called SU3 symmetry. This means that if we change the quark from the U quark to D quark or to S quark, they have same strength of the QCD. This is called SU3 flavor symmetry. And they don't have a relation with the CP violation or C violation or P violation. We just use it to how to say, to let our calculation become more simple. It's just a way to simplify the calculation. And actually they don't have a relation with the CP violation.
It's an approximate symmetry in strong interaction. So you do expansion around this approximate symmetry. More questions? I have a question. In your conclusion, you said that there are 2 processes that might deviate from the standard model.
Yeah.
Is that how many sigmas deviation?
Actually, I said may have. Let's still have some. This is for example, these 2 numbers. Actually, this is a 1 sigma range. Actually, they may have broken, but they still cover a very tiny range. So let's still not. It's a sign. Maybe when we have a more reliable data or precise data, we can say that they have broken the standard model.
Okay. Currently, it's like 1 sigma deviation.
Yeah, but still, now it's still not.
Okay. More questions? Okay. Okay, let's thank Xiaofeng again. And thanks for coming. And so let's hope the young people can keep doing excellent work. Thank you.